Hello and welcome to Honors Physics. I'm Dr. Bonner. I'm your physics teacher, as you know, and you've made it here to the first video that you'll ever have to watch. And today we're going to go over how to collect data that will give us confident findings and easy interpretations. So let's get going. So when we try to ask ourselves, how do we collect good data? What we should have fleshed out when we first just started collecting data with the pendulums were a couple techniques that are going to allow us to have more confidence in our data. And so those three techniques are that we can use as we're collecting data to ensure that we're going to have more confident trends or findings from our data would be to maximize the range of the values you test. We want to choose a lot of different values to test, and then we want to do at least some sort of repeated trials to some extent in order to increase that confidence as well. So we're going to get going one by one through these. So we're going to start with maximizing the range of values tested to explain how we do that and what that means and why it's important. So first thing we have to realize what we mean by range of values tested is what we know to be the independent variable. So in any controlled experiment where you have a independent variable and a dependent variable that you're measuring, and you're trying to see if there's a cause and effect and in which way one variable affects another, this is often used in graphing. Then the one variable that you choose the different values for to test is referred to as the independent variable. It's independent of any experimental effects. It gets its value from your choice of whatever value. So we're going to choose a wide range of points. Don't choose points that are all really close to each other. Like extend it out as much as you can over a large range. So we're going to refer to that range of the values we test as a data set's variance. So easy way to figure that out is what's the difference between your highest value that you chose and your lowest value that you chose? And that's going to be a way that we can quantify this maximized range of values tested. So let's take a look at these three different sets of data that were on whiteboards. These all were pendulums experiments, but it doesn't really matter. We're just going to look at it as just raw data and interpret it like which one did the best job. And so we want to look at which of these three examples had the largest variance. And so what we're looking at, let's look at 1A first, is what's the independent and dependent variable? So we're testing different string lengths, and then we're trying to figure out what the swing time was. This is from the pendulum experiment that we just did. So our highest value of the choices for length that we did was 74, lowest value was 14. And so if we want the variance, again, we're going to take the difference between those two. And that means that the 74 minus 14 will give us a variance of 60. If we look at B, again, this is going to be lengths. Now they tested each length twice, but I just want to look at the independent variable, which is that length. And so of the four different lengths they chose, 70 was the highest, 13 was the lowest. Subtracting those two to get our variance would give me then a variance of 57 centimeters. And in C, again, this was the same experiment with the length versus time. Doesn't matter what the experiment is. What we're looking at is what's the independent variable and how much of a difference do they have in the highest and lowest values. So our highest value was 63, lowest value was 9. Subtracting those two gives us a variance of 54. Okay, so which one of these had the largest variance? And so we know that of the variances we found, A was the best. Yay, good job, yay. Okay. So not too bad there. Now, maximizing the range of values is going to help us to see if there's a relationship and to really see that. It's kind of, if you imagine a graph, it zooms out on the graph so that we can see that shape of the graph better. And it just gives us, instead of looking at a little postage stamp of data, it really broadens the data set so we can see the bigger picture. So now that we've got that explained, let's look at how we test different values and why that's going to be important. So we want to test a wide range, but we also want to get as many individual different values within that range tested as possible. This would represent, if, for example, on a graph of how many different data points you're plotting. So we need as many as you can. I mean, it's great to have a 500, or why not 1,000, or why not 5,000? You're going to be limited on time in terms of like what you can do in a single experiment with class time, but we shouldn't just do a few and then stop. I mean, we should be doing at least 5 to even. Okay, so let's take a look at these three examples. And so the question here would be, which of these three examples of data tested the most data points? So we need to look at the independent variable and see how many data points do you see. Come on, everybody, count with me. We got 1, 2, 3, 4. That's not very good. We need at least 5, and 5's not that great. What about B? How many data points do you see? Come on, everybody, count with me. We have 1, 2, 3, 4. Not good. And then C, we got 1, 2, 3, 4, 5. So pretty good, right? I mean, that's 5, and we'd say, okay, that's going to be the winner. It definitely has the most data points, but 5's not that great. So I'm going to give it a neutral face there. We'd like to collect as many points as we have time to collect points. So if you get 5 done, don't stop. Just keep going until we don't have any more time left in class to collect data. So now that we've looked at maximizing the range and testing a lot of different values, let's take a look at repeated trials, which there's a lot. Repeated trials are really important. So they're important for a variety of reasons. And so what we're going to do with repeated trials is we're going to keep the setup identical. We're not changing anything. We're just going to repeat the same data point a couple times. And that should give you the same measurement, right? If I don't change anything, then I should get the same, for example, swing time, right? If I keep the length the same and I just repeat it and repeat it and repeat it, I should get the same swing time. But as we know, we don't always get the same swing time because there's error, right? So by obtaining repeated trials or a set of repeated trials, we can obtain then the average of those. And that's going to be what we're going to use as our measurement, is the average of the repeated trials. That's actually going to be more accurate than any individual value because you're averaging all of the individual values, each of which have error, and you're taking like the middle of those, which is likely going to be more accurate than any individual one. We can also calculate the amount of error that we have, which we can refer as error, but really we call it uncertainty. And that we can find by doing the difference between the highest and lowest values like we did with variance. But with these, it's mathematically the same, but different because we're using the repeated trials data set. So these values that should all be the same. Well, what's the difference between the highest and lowest values since they're not exactly the same? That would give us our uncertainty. Okay, so it's very important that we have that from repeated trials thing. Okay, and then if we have multiple different data points that we have repeated trials, like each length has repeated trials, then we're going to use the largest uncertainty value as our uncertainty. Okay, so lastly, we're going to have to unpack a lot of this, right? But that allows us then to determine, is there even a trend in our data, right? Is Y affected by X, right? So otherwise, our graph could just be like a flat line, really meaning the Y is not even changing no matter what value for X we choose. And so we have to, before we just graph and assume that there's just everything affects everything, we have to determine, is what I'm varying, the independent variable, actually even affecting the Y value? And we're going to take a look at that. And we often just kind of over the years have referred to those as trend, no trend types of questions. So let's unpack this a little bit. Okay, so a trend is going to if you think about this, trend is going to be occurring if your dependent variables overall change, the range of it from high to low, is much bigger than the range of the repeated trials, right? I mean, if you think about like, is my change in my Y value much bigger than the random changes we saw in the repeated trials, which we call the uncertainty? If the uncertainty is pretty close to the range of values that we saw, then we can't really determine that any changes weren't just due to error. So that's how we do the trend or no trend, okay? So let's take a look at a couple examples. So what we want to look at here is which of these 3 sets of data have the smallest uncertainty. So as I look through the repeated trials, I'm going to look for the highest and the lowest. So that's for one washer. When they used 5 washers, they had repeated trials there, and the highest one and the lowest one were 1.95 and 1.66. And then when we used 10 washers, the highest and the lowest were 1.87 and 1.8. So of those, I can already see that these are going to be the biggest difference, and that what I'm going to use for uncertainty is 2.23 minus 1.83. That's 0.4. In B, we have 1.8 and 1.37 down in angle number 4, the 4th data point. Those were the farthest apart compared to any of these other repeated trials, the 1.8 and 1.37 were the farthest apart. And so that's going to then give me an uncertainty of 0.43 when I subtract the difference between those two. And in C, the values that we have here that are the farthest apart are going to be 1.59 and 1.25. That's going to be for the 60-degree angle. Again, the rest of them are not that far apart compared to this one on the top, which would mean that the uncertainty there when we subtract 2 is 0.34. So which one of these has the smallest uncertainty? You got it. Yay. Good job, C. You did a good job there and got the smallest uncertainty. But really, you just do the best you can. We want to minimize the uncertainty as best we can. But if you have a lot more data, then you're just going to have to rely on maximizing the data range and collecting multiple points to really make sure you can see any changes that might be occurring. Now I'm going to replace B with this one. Okay, and what we're going to try and do here is we're going to try and do the trend or no trend question. So we're going to use that uncertainty value that we just found to then see, does that show a trend in the data based on the uncertainty? So for example, we're going to be asked, does the number of washers affect the time? Right? Is there a trend where it affects it? Or is there no trend, meaning it doesn't affect it? Does the length that we choose affect the swing time? Or does it not? Again, is it trend or is there no trend? And then does the angle that we choose to release it from affect the swing time? And yes or no. So we're going to use the data to show this, not what our intuition thinks. And the way we do that again is going to be to compare the overall range in the time values, right, our dependent variable, and compare that to the identical repeated trials variations that we have, which we call the uncertainty. So let's look at A. So first off, uncertainty we can find by doing the highest and lowest values from the repeated trials. And the highest and the lowest values, right, are going to be then used to get the uncertainty. And then since we have 3 different uncertainties from 3 different sets of repeated trials, we're going to use the one that's the biggest, and that's the 0.4 like we talked about. So does the number of washers affect the time? No, it does not, right? Because if we look at the averages of these, which they didn't calculate and they should have, then the averages here would be 2.04. The smallest of these would be 1.81. And so that gives me then a dependent variable, the seconds from highest to lowest that we saw for the various different washers ended up being a difference of 0.23. When we didn't change anything at all and just kept it with one washer, we saw changes of up to 0.4. So that means that this 0.23 is not any bigger than what air could cause, and therefore there would be no trend, meaning the number of washers doesn't seem to affect the swing time. And you can see here that that's what they thought too, right? All right, so let's look at B. Now, when I go to try and calculate the uncertainty, I notice that they didn't do repeated trials, so I'm dead in the water. I can't do anything. This is just worthless. I have no idea how to do trend or no trend. It can't be answered with any certainty. But if we do ask this, and the group made a response, what'd they think, right? So they said the shorter the string length, the less the time it took to go back and forth. So they determined that, in their opinion, there was a trend, but the data can't support that unless we have an idea of how much uncertainty is there in the time values. So answer here would be, we actually can't answer this with confidence. You're kind of estimating that you think it is based on how much you think the time values can be off by. Assuming the time values can be off by several tenths, this looks like it's changing by more than a couple tenths as it goes from 1.52 to 0.6. But we can't confidently say that because we didn't actually get that uncertainty in the time values. All right, in C, we're going to look at the uncertainty. And so we have a bunch of different values. We have 10, 20, 30, 40, 50, and 60 degrees that we tested. And each of those has 2 repeated trials. You want to do more than 2 ideally, but this is fine. So when we calculate the uncertainty by just doing the difference between those, the largest uncertainty is that 0.34. So we're going to use that for our uncertainty. So do we think that the angle affects the time? Well, let's see. The averages of these values, the highest average was 1.42 up here. The lowest one was the 1.06. So when we subtract those, we get 0.36, which is technically bigger than our 0.34. So what do we say here? Right now, the thing that we have to realize is this is not a big difference. So am I confident that, oh yeah, 0.36 that's definitely not due to error, because error can cause only 0.34. It's like, come on, right? It has to be much, much greater. That's why I put the 2 greater than signs. It must be much, much greater, like significantly greater. And so I would say that no, or at least it's too subtle to confidently conclude, given the sensitivity of the experiment, meaning like how much error we have, to really confidently conclude that there's a trend. So I would say probably not. Let's see what they thought. So on their board, they said release angle and the time did not significantly affect each other. So they agreed with that. All right, so let's put it all together into one question. Given this data, let's provide feedback on the data collection methods based on those 3 data collection techniques. And if there are repeated trials, we're going to determine the largest value for the uncertainty. And then we're going to determine if there was a trend in the data or no trend based on the uncertainty. Okay, so we're going to just list out those 3 techniques that we just talked about, and we're going to say, like, did they do it, yes or no? I often will just use like a happy face, frowny face on these just to assess. So did they maximize the range of values tested? Maybe. So I think this is kind of like I would say not great or neutral. It's kind of hard to say because without the context of the experiment, like is 50 is most they can do? So I would say probably not. You could go to like 5 centimeters or maybe 60, 70 centimeters. They test a lot of different points. I only see 4 there, so that's not very good. Did they do repeated trials? They did. They did 2 for each one, so that's good. Happy face. And so now we're going to go ahead and determine the largest value for uncertainty. So the biggest difference in the repeated trials of those 4 different points was the 0.8 to 0.91. So that would mean our largest uncertainty was 0.1 seconds. And so now if we assess, is there a trend in this? I would say yes, there is a trend, because if we look at the average values for all these different 4 values, the average went from 0.85 to 1.68. And so that would mean that the difference here, 0.83, is much bigger than the 0.1 error. And so that would mean there is a trend. All right, and that concludes our video. I hope this was helpful, and I'll see you later. Have a good one.